Thank you.
Thank you. Thank you. Hey, cheers. Thank you, Rahul, for the introduction. Will robots take away our jobs? What's going to happen to the people? These are some of the questions you normally see when people talk about robotics. It is a controversial topic, but today I would like to make a case that we do need robots going forward. And hopefully by the end of this talk we will all be on the same page. Ladies and gentlemen, good evening. My name is Rahul. It is my pleasure to be one of the speakers this evening, and I will be talking about the future of robotics in our growing sector. Before I begin, I would like to acknowledge Ministry of Business, Innovation and Employment for funding this research project. Without their support, this would not be possible. I would also like to acknowledge our research partners, University of Canterbury, Auckland, Otago, Lincoln Agritech, Plant and Food Research. Just to set the scene as to why do we introduce robotics in the apple growing sector is because this industry is in a booming phase at the moment. It contributes $850 million a year and is expected to become a billion-dollar industry by 2022. And our apples are also very popular overseas, such as the New Zealand Envy apple was voted one of the favorites amongst the US consumers. World Apple Review has ranked as the top performer for the last 4 years in running. It takes into consideration such as production rates, infrastructure, innovation, and so on. We compete in countries like USA, Mexico, Chile, and so on. Billion-dollar industry, popular apples, they're all hanging on a thread because of this. We see headlines like this every year. This industry is also crippled with labor shortage issues. One orchard in Hawke's Bay reported they cannot collect 200 bins of apples off the trees just because they cannot find people to do it. Another orchard in Nelson this year, they had a chemical thinning failure, which meant they had more apple fruitlets which had to be picked up by manual labor, which ended up costing them $100,000 over budget. Now, one is the labor shortage issue, and the other issue you have is with the imported labor. Most of the work, if you go into an orchard in New Zealand, most of the workers you see are from overseas. It adds another extra layer of complexity because these are seasonal in nature. Every year when the season kicks in, farmers will have to organize this, and it's just extra costs. Similar challenges are faced by overseas growing countries such as the USA. The Americans, they managed to put a robot on Mars, but not a single robot in sight in the apple orchards. Every year in Washington state alone, 15 billion apples have to be hand-picked with an operating cost of $1,150 per acre. For the record, USA has about 300,000 acres purely dedicated for apple growing. It shows the enormity of the industry. To add to that, manual labor comes with a lot of health and safety issues, such as back strain injuries and musculoskeletal injuries. $21 million were paid in compensations in Washington state for just 1 year. Our farmers are trying to address these issues. They are changing from a traditional 3-dimensional tree to a 2D canopy. If you go to an apple orchard in New Zealand, this is what you will see. What this has done is it made it more attractive for the workers. The fruits are more exposed, it's easier to harvest, and it's easier to thin. And it's easy for a human to harvest. We predict it'll be easy for a robot to do it compared to a 3-dimensional tree. So my main research focus in the apple growing sector is apple fruitlet thinning. Why do we thin fruitlets? To allow the remaining fruits to grow bigger and healthier. They come in clusters of 3 to 5 and they're sent back to 1 to 2. The season lasts about 7 weeks, beginning of November, and then 7 weeks from then on. If they can find people, they finish in 7 weeks. If they cannot, they go on until it's all done. And this is how harvesting and thinning is done in our orchards. About 4 workers are placed on a hydraulic lift to harvest the top half of the canopy. The remaining ones cover on foot. Thinning is done holding it in your palm and using a shearing movement with your thumb. And it has been reported that bruising can occur even with manual labor. The current growing sector presents us with an engineering opportunity to put robots in an orchard. It also gives our entrepreneurs a chance. As it turns out, agriculture robots are not very popular. These are the number of hits we receive on Google Scholar. As you can see, the service robots are more popular compared to the agriculture ones. So there's a huge gap to fill in the agriculture sector. If you look at other industries, innovation has occurred much before there was a need for it, such as Uber, Amazon, and Netflix. Whereas agriculture, we're getting started now, after there's been a call for help. So obviously there's a huge gap. And if you look at the startup companies in the last 5 years, just within New Zealand, none of them are in the agri-tech sector. So it's another opportunity for us to close in on. This is the hard part. Probably explains why there aren't many people opening companies in this sector. Orchards are very unstructured and dynamic. It's harsh, there's wind, there's rain. Things can change in an instant, which a human can easily adapt. Robots, it can be a big ask. Which apple to pick, which fruitlet to thin. These are some of the decisions a human makes based on its shape, color, size. It can be a big ask for a robot to make them. Growers lose up to 1 to 2% of yield from bruising, from manual labor, and it can go all the way up to 15% if left unsupervised. So we know it is a very delicate task, and it is also, and surroundings are prone to damage. The solution: design and build a commercially viable robotic thinning machine. But what does it look or sound like? What does it mean? It should be able to mimic all this human decision making. What a human is making, the robot should be able to handle those decisions, such as which fruitlet or which apple to pick. We need machine vision stuff, like human uses eyes to locate where the fruits are. We need machine vision on there. And obviously a sense of touch to delicately grasp the fruit so it doesn't damage it. And for that to be a reality, I believe these are the main breakdowns: scanning, crop detection, grasp selection, attachment, and detachment. My main research area will be within the things covered in the box. Grasp selection is determining what's the best way to approach a fruit from. Every fruitlet is going to be different from the previous one. So a robot will have to make those decisions as it sees a fruitlet, what's the best way to go about doing it. Attachment is holding onto a fruit without damaging the surroundings. And detachment is removing it off the tree. And the way we do those parts is we use end effectors. End effectors are grippers which are used at the end of a robotic arm. This is one of the most overlooked components in robotic research, and is one of the components that is holding back the robotic revolution from going forward. They're very popular in industrial applications. You can buy them off the shelf, but you can't use them in agricultural sector. They're not very suitable. They're mostly suitable for pick-and-place objects. But where I want to take with this talk is I want to show you a bunch of case studies. How do we design and build a machine that has never been done before? We'll look at what other people have done in other sectors, such as the cherry fruit harvesting. This machine was developed in Japan to address labor shortage issues. Cherry fruit is a very delicate fruit. It is easily prone to bruising. It uses a custom end effector, it uses a custom arm, and they've developed it from scratch as well to prevent bruising. But they've tested it out in field with less than acceptable commercial viable thresholds. It can happen. China is also one of the countries facing labor shortage in agriculture. They've developed a tomato harvesting machine. This is one of the smartest machines I've come across in my case studies. It uses a gas bag, as in a balloon, to hold a tomato together as the tomato enters into the cylinder. And then it sends a signal to cut the stalk. This is a sweet pepper harvesting machine developed in collaboration between Israel and Europe. It has a custom end effector, but it uses off-the-shelf robotic arm. It has a longer cycle time, but hey, this can work 24/7. A human won't be able to work 24/7. It has a 61% success rate. Selective harvesting, as in they've modified the crop quite significantly to be able to harvest it. This is another harvesting machine developed by Queensland University of Technology in Australia. Again, it uses a custom robotic arm and it uses an oscillating cutting blade. The main issues with this machine is when you grip onto fruit, it thought that it has the fruit, but in reality it didn't. And in the cases where it thought it had the fruit, it ended up cutting those sweet peppers and bruising it. From the case studies, it is apparent most of these machines were developed to address labor shortage issues. Robotic thinning has never been done before. That means we have to establish a few facts from the ground up, such as when does bruising occur? What is the force values that this is occurring? Humans, we have 7 degrees of freedom on our arm. How many degrees of freedom does my robot need to have? What's the best way to approach the fruit from? Orchards are dynamic. A slight change in wind can change the position of the fruit. Do I need a vision system on the hand itself? Do I need more vision system to accommodate for those errors? And this is how we answer all the hard questions. I made that smart sensor glove. It can give me the force values that as I'm holding a fruit, it can give me that in real time, and we gather the data. And when we build a gripper, we integrate those sensors onto a gripper and create a control algorithm to have the delicate grasp onto fruit. From case studies, people have used soft materials to minimize bruising. I made that gripper 3 days before coming here, so I'm just testing out different iterations, as in what's the best way to grab the fruitlet. This is us doing some tests in the lab to see what's the best, testing out different approach angles, and yeah, seeing how many degrees of freedom. From this test, we were able to establish we definitely need more than 2 degrees of freedom. When we first went to the orchard, we saw the 2D canopy, and we were under the impression that we should be able to get away with X and Y, but that is not possible. Every year, we have 7 weeks of window for fruitlet thinning and harvesting. How do we prepare for it for the rest of the year? We use 3D printing. We have a range of different 3D printers in our lab. This is a 3D printed tree branch designed by my colleague. It mimics an actual tree in Nelson. And this is where we do all our testing on before we go out onto the field. Here's some success stories from the past done by our students. This is done by a team of 4th-year engineering students. It's an autonomous vehicle that is designed to navigate around in an orchard. It uses LiDAR sensors and it's completely autonomous. This is a most recent success story. This was Matthew Peebles, PhD, and Josh Barnett designed and built the hardware. It just came back from California from field tests and was back in time for display at field days. They did a fantastic job on this one. It's something for us all to be proud at Waikato. They're addressing the issue of labour shortage in asparagus. We have an opportunity here at our doorstep. As a country, this is our opportunity to become global leaders in agricultural robots. We need robots more than ever before. Our farmers needed it yesterday, and we are working on it. And obviously, there's also a gap for entrepreneurs to close in on, because no one's doing it, and if we're not doing it, and if no one else is doing it, we have to do it. Thank you, ladies and gentlemen. I hope you've enjoyed a bit of robotics research overview at Waikato, and I'd like to take any questions if you have any. Thank you very much. Thank you, Rahul. Thanks.
That was a really nice presentation.